The point of today's lecture is to discuss the superconformal index. Okay, the reference for today's lecture is in today's lecture I'll stick to d equals 4, and the reference for today's lecture is one. This is a paper I wrote along with Suvrat, Maldasena, and a student called Kinney who left the field after this paper. Okay, okay, okay. So, okay, fine. So, what I want to argue for you is that superconformal representation theory. Okay, what I want to argue for you is that superconformal representation theory gives you powerful dynamical statements about interacting quantum field theories. Okay, and I'm going to try to make that argument by defining a sort of index for you that is protected under energy renormalizations. Okay, so the first thing I'm going to do is to explain what the corresponding situation is for the conformal algebra, and try to show you that the same thing does not happen for the conformal algebra. Okay, so consider SO 4, 2. Okay, this is the 4-dimensional conformal algebra. As we have explained, representations of the conformal algebra are labeled by representation of SO4 and a scaling dimension. This gives labels for the primary states, and then the whole module follows by acting on this primary with momenta. The descendants follow by acting on this primary with momenta. Right? So, therefore, in this situation, representations of the conformal group are labeled by J1, J2. These are the SU2 times SU2 integers, because SO4 is SU2 times SU2, times some scaling dimension epsilon. Okay. Now, as as in this language, momentum, which is a vector, please.
I left my charger.
Okay, in this language, momentum, which is a vector, remember, a vector is a bispinner under SU2 times SU2. So P mu has dimension under SU2 times SU2 is in the half-half representation. Okay, great. So now suppose we consider some primary state which is labeled by J1, J2 and epsilon, and we look at level 1 states, okay, which are P mu on this guy. Question: what are the quantum numbers of these states? Okay, so that's clear, just Klepsch-Gordon. Okay, we will get J1 plus minus half, J2 plus minus half. These two plus minuses are independent of each other. Right, you could get plus here and minus here and so on. Okay, and epsilon naught. This has these quantum numbers. So, at least if J1 and J2 are not 0. In the case where there's 0, the minus half doesn't exist. If J1 and J2 are not 0, the quantum numbers of the states that you get, you get 4 different representations of SU2 times SU2 times scaling dimension. And of course, sorry, I should have said plus 1. Epsilon naught plus 1. Right? Now I've already explained to you last class that the norms of these states are constant within a given representation, but depend on which representation we're working. Okay? And when you compute the norms of the states, you find the following. You find, okay, so epsilon naught plus 1. Okay, in fact, I've been precise in this paper. The norm squared by 2 of the states is given by epsilon naught minus J1 minus 1 plus delta. Let's first look at, okay, the norm that is maximally negative, that is, that gives you the maximally stringent criterion, is the guy where you, as we've discussed last time, take the j's negative. So now let's look at the guys for these guys. Let's look at the special guy because it's going to give us the most stringent condition. And let us suppose for a moment that J1 and J2 are not equal to 0. Neither of them are equal to 0. Okay? Then when you compute the norm of the state, you get epsilon naught minus J1 minus 1 minus. Okay, this is the norm that you get. Okay. So this tells you that epsilon naught has to be greater than or equal to Is this clear? Okay. Now, if you work out the same calculation for J1, either J1 or J2 or both equal to 0 at level 1, okay, there you have to do the calculation differently because suppose J1 was equal to 0, you would have to take the J1 plus half. And if J2 was equal to 0, you'd have to take the J2 plus half. Okay? You find epsilon naught is greater than or equal to J1 plus J2 plus 1. Okay, this was, I think, in the case where either J1 is equal to 0, but J2 not equal to 0, or vice versa. Okay, and the difference between these, so this was of course J1 plus J2 plus 2. The difference between this J1 plus J2 plus 2 and J1 plus J2 plus 1 is that one of these J's, you don't have the minus half, you have the plus half. That makes the difference. Okay, now in the case that both J1 and J2 are equal to 0, okay, in the case that both J1 and J2 are equal to 0, you find indeed that epsilon naught has to be greater than or equal to 1. And, you find your first non-trivial condition at level 2. And that becomes that E into E minus 1 is greater than or equal to 0. This is the case J1 equals J2 is equal to 0. Okay? So this gives you that either E is epsilon naught, epsilon naught. So either epsilon naught is equal to 0, that's the identity operator, or epsilon naught is greater than or equal to 1. This is something that we've seen previously, right? Scaling dimension for a scalar field always has to be greater than d minus 2 divided by 2. Okay, so this is the full set of unitarity constraints in 4 dimensions that follows from the conformal algebra. This was the case J1, J2 not equal to 0. This was the case when one of them was equal to 0. And when both of them were equal to 0, we got this case. So in other words, both of them are equal to 0. This bound is obeyed. But there's also the possibility that epsilon is equal to 0. Okay?
This comes from second level.
The second one comes from a level 2 constraint. And the null state corresponding to epsilon naught equals 1 is not a level 1 null state. It's a level 2 null state which is p squared. Okay, Excellent. So, now what I want to focus on is the following. What I want to focus on are the representations. What I want to focus on are the representations where this bound is just exactly saturated. Okay? The generic representation obeys these bounds as an equality. As an inequality. Whereas if you're on the edge, this bound is obeyed as an equality, and this is non-generic. Okay? So now I'm going to give you some notation. Okay? Let's use the notation A, E, J1, J2 for a generic long representation. Okay? This long representation is primary with energy E. What I called epsilon naught there is now E, and has angular momentum J1. Okay? On the other hand, let us use the terminology.
What is this A as a quantity? Just the symbol.
It's just a symbol. Symbol that denotes that kind of representation. Okay? Now B left J1 is the short representation let's use C J1 J2 to denote the short rep with J1 J2 both not equal to 0. So J1 not equal to 0, J2 not equal to 0.
So this is when the bound is set.
Yes, this is when this bound is saturated. So in the notation for this representation, we don't need to indicate the energy, because the energy is J1 plus J2 plus 2, because that's where it's saturated. Okay? There is one less label on this. Then we will also use the following notation. Let's call BJ1, and let's put an L here, the short rep with J2 equals 0 and J1 not equal to 0. Okay? Similarly, we'll denote BJ2 and we'll call it R as the short rep with J1 equals 0, J2 not equal to 0. Okay? And then finally, we call the short representation, we define just B to be the representation with 1, J1 equals J2 is equal to 0. Okay, apart from the vacuum E equals 0, which never enters in our analysis, so we won't give it a name, these labels cover every short representation of the conformal algebra. Is this clear? Diksha, what? L says that this is for J2, J right equals 0. So which of it's labeling the two SU2s. Okay? So L, for instance, is the one where the J for the left SU2 is not equal to 0, but the right SU2 is equal to 0. That's why L. And similarly for R. Clear? Okay. So
when the B's saturated?
What? These B's obey this equation. Okay? And therefore, the energy of B, the charges are J1, 0, and J1 plus 1. Okay? Left angular momentum is J1, right angular momentum is 0, and energy is equal to J1 plus 1, because it saturates that bulk. Clear? Okay? So these are all the representations, all kinds of every representation of the every unitary representation of the superconformal algebra appears on this list, apart from the vacuum, which is a very trivial representation, will never do anything interesting.
If epsilon naught is not A2 plus naught,
then it's one of the A's. This is a generic long representation.
but you say A is only for J1, J2 not equal to
No, A is for anything. Any long representation, anything that does not saturate a bound is an A. Okay? The other representations are those that saturate a bound. Okay, great. Yes? Long representation means a representation that has as many states in its module as it could possibly have. In the case of the conformal algebra, what it means is that the full partition function of that representation is the partition function of the primary times the partition function of every derivative. We wrote down these partition function formulae some class. So every state that you can make by acting unrestrictedly with p's gives you a distinct state. That's a long representation. Okay? Short representation is when, what happens is when some p's, some combination of p's annihilates the state. Clear? Okay. Now, what I am going to do is to write down character formulae for each of these representations. So remember, we talked about the characters of these representations last some class. The character was trace x to the power, let's call it e here, y1 to the power j13, and let's say y2 to the power j23. In this case, we have two chemical potentials for internal symmetry that we need to take into account. Okay? And to answer Kanu's question a little better, if we had a primary, and in the case of a long primary, the partition function, the character of an A, j1, j2, epsilon naught, is very simple to write down. It's just x to the power epsilon naught. Then SU2 character, chi j1 of y1, chi j2 of y2. These are the SU2 characters. Okay, divided by 1. Now in this case it is, how does it go? Right, 1 minus x y1 y2. Probably the way I've defined it, square root to the half. 1 minus x y1 to the power minus half, y2 to the power half. Everything's in the denominator. 1 minus x y1 to the power half, y2 to the power minus half. 1 minus x y1 to the power minus half, y2 to the power minus half. You understand this? Because these are the charges of each of the derivatives. The derivatives act in an unrestrained way. Okay, so it's very simple to write down the character formula for a long representation. Precisely because it's a non-interacting problem. You take the primary, its partition function, and then you write down the partition function of the first derivative times the partition function of the second derivative times the partition function of the third derivative times the fourth derivative. You understand that the derivatives have charges plus minus half under the two y1s. That's why this y1 to the power half, y1, and so on. Is this clear? Kanu, is this clear? This is a long representation. The characters are there. Okay. Now I want to write down the characters of the short representations. Okay? So the characters of the short representations are actually very easy to write down. Well, how are they easy to write down?
Sorry, can you explain this formula?
Yes. This formula? Okay. You take the primary. That has this character. Is this clear?
Yes.
And then on that primary you can act with any one of the four derivatives any number of times. Each of these factors, when you expand it, is the action of each derivative arbitrary number of times. You expand it, there will be a term where it acts once, or twice, or thrice. Okay? And the fact that no combination of derivatives kills this primary tells you this is the correct formula. That's why it's a generic long representation. Very simple. Much easier than SU2 theory. You see, SU2 group theory or finite Lie algebra theory is complicated because you start with the lowest weight state and then you keep acting raising operator. At some point you annihilate things, right? So characters are quite difficult to write down there. Here it's trivial. Just keep acting. All good? Now, what I want to do is to take into account the fact that we deal not just with long representations, we have not just long representations but also short representations. I want to write down the characters of the short representations. Okay? So, how do I do that? Well, consider, let's say, the C-type representation. What are the quantum numbers of the null state, the state that is annihilated by the C-type representation? Well, remember that the C-type representation had quantum numbers J1, J2 and epsilon naught. The quantum numbers of the null state for this were J1 minus half, J2 minus half and epsilon naught plus 1. You got it by acting with the momentum and contracting in this particular. Now notice that if epsilon naught equals J1 plus J2 plus 2, then epsilon naught plus 1 is greater than, strictly greater than, J1 plus minus half plus J2 minus half plus 2. Right? Let's see this. Epsilon naught plus 1, let's compare this with J1 minus half plus J2 minus half plus 2. Okay? But this is equal to epsilon naught plus 1 and this was J1 plus 3. No, sorry, plus 2. J1 plus J2 plus 2 minus 1. Okay? Epsilon naught was greater than this. Therefore, epsilon naught plus 1 was greater than this. Therefore, epsilon naught plus 1 is greater than this minus 1. So you see that this is greater than, sorry, not even, greater than, strictly greater than epsilon naught. Is this clear? So the null state that you created has quantum numbers such that this null state is itself a long representation.
So that will give a full geometric series.
Something like that. Let's see. Good. Okay. Now, all we want to do to get the character of this representation is, had it been a long pretend it's a long representation, and then remove all the states of the null states, or all the states coming from null states and its descendants. So remove the character of the primary of the null states. Okay? So now I'm going to, what I just said in words, I'm going to write down as an equation. Okay? So I'm claiming that chi of C, no, this was called a C, right? J1, J2 is equal to chi of A, J1, J2, J1 plus J2 plus 2 plus epsilon. Limit epsilon goes to 0 minus chi of A, J1 minus half, J2 minus half, and epsilon naught, so, J1 plus J2 plus 3. Okay? What is the first term on the right hand side? It's simply the character of the state of the primary with these quantum numbers, pretending that it was long. Right? That's this limit epsilon goes to, there aren't really long representations when epsilon is 0, that's why we have to take this limit. But you just take the state with J1, J2 and E, that's a long representation, then take the limit epsilon goes to 0. Okay? And once you've done that, that would be the state with those primary quantum numbers had it been a long state. The character of that state, had it been long with those quantum numbers. Yeah? And then you remove what you added in extra, namely the character of the primary, of the null states. But you remember that had quantum numbers, J1 minus half, J2 minus half, and whatever epsilon naught was, plus 1. But epsilon naught was J1 plus J2 plus 2, and therefore that's become J1 plus J2 plus 3. Is this clear? Why is the limit there? It's because there is no long representation at epsilon naught equals 0. Long representations only exist for E greater than J1 plus J2 plus 2. So to write A of J1 plus, at that is a meaningless thing. But the limit is meaningful. And the character has a limit. Is this clear?
What is the subtraction?
The subtraction is the... Why is it plus 3? You remember how we got the state. We started with this primary, J1, J2, and J1 plus J2 plus 2. We acted on it with a momentum. That changed this to 3 and reduced each of these by half. Okay? That's why that's... You have to remove it and all its descendants. And therefore you remove the whole character of this. Now notice that this null state was itself a long state. So its character is of the simple sort. Null state is also primary because it cannot be written as P times some other null states, the first null state, the problem. Okay. But P times this will also be null because whatever inner product you get by these extra P's and K's, it will multiply the norm of this state, which was 0. Right? This PK algebra gives you that the norm of the descendant is something which you can calculate times the norm of what you started with. But if you start with 0, you always get 0. There's never an infinity in this game. Okay? Clear? Why are we removing the character of the null state? Good. You see, these states had 0 norm. Okay? So they existed as states. The theory was not unitary. Okay? However, it could be that what happens is that there's just an equation in the quantum field theory saying that these states are 0. So these 0 norm states are just 0. That's what happens typically. For instance, we studied 2 or 3 examples in one of these classes. The null state at level 2 for a free scalar was the equation del square on scalar is equal to 0. That was the free field equation of motion. The null state at level 1 for a conserved current was del mu j mu. Yeah, and that was just 0. So that's how these null states can possibly appear in physical theories. If these short representations can. If the null states are just 0, there's an equation of motion in the theory that tells you these states are 0. That's why we're removing them, because they're not there. Right? Had they been there, they couldn't have appeared, these representations couldn't have appeared without the null states being 0 in a unitary theory. Because in a unitary theory, the only state that has 0 norm is the 0 state. What? That's why we are removing it. But of course, the field theory will have to do it dynamically.
As a representation, they exist as a long representation, but this field theoretic thing,
yes, they exist as a long representation, but not a unitary long representation. So if they occur in a unitary field theory, they'd better just be removed. Okay? Fine. This kind of thing happens all the time, right? When we do BRST quantization, it happens. You know, it's standard mechanism in physics. Right? Okay, excellent. Fine. So you understand this equation now? Okay? Similarly, we can suppose we take a B-type representation, BLJ1. Okay? This is equal to chi of, this is equal to chi of, now in this case, we get A J1 0 J1 plus 1 plus epsilon, limit epsilon goes to 0, the long representation with energy just above the short representation, minus the character of the null state. Now in this case, what was the null state? You see, J1 was non-zero, so J1 was reduced by half. But J2, which was 0, had to be increased by half. So we get chi of A of J1 minus half, and J1 plus 2. For this statement to be consistent, we have to check that this is indeed a long representation. Okay, let's check. For it to be long, we need that J1 plus 2, that's the energy, has to be greater than J1 minus half plus half plus 2. Maybe I got it wrong. Yes, I think you're right. That this was a C type. This was a C type. Sorry. So it was equal to. Okay. So let me just. Yes. It is. Yeah, exactly. B. And a C type representation. Okay, excellent. Okay. What about chi B right J2? That's similar, right? That's limit epsilon goes to 0. A J1, 0, J2 plus 1 plus epsilon minus chi of a C type representation with half, J2 minus half, and J2 plus 2. Okay? And finally, we need the character of the B-type representation. The B representation, the scalar representation with the scalar representation with dimension 1. Okay? But chi B, this is very easy, is equal to chi of A type J0, 0, 1 plus epsilon, limit epsilon goes to 0, plus minus chi of A0, 0, 3. Okay? Reflecting the fact that the null state in this case is p squared on that. So p squared increases the dimension by 2, doesn't change j. Okay? So we started with j1 equals j2 is equal to 0, which remains j1 equals j2 equals 0. And then the dimension of b, which was 1, the null state now becomes 3. This is clearly a long representation because 3 is greater than 1, basically. Clear? Okay? Now these formulae here, give us accurately the character, is now a complete determination of the character of all representations of the conformal algebra. How? The first formula here, allows us to compute C-type characters. Because it's a difference of two A-type characters, and we already know the A-type characters.
In the last formula, how is epsilon plus 1 greater than 2?
It's not greater than 2. It's greater than 1. No, it is an A representation. You see, whether you're an A representation or not is determined by whether you're above the bounds for those J's. The bounds for 0 and 0 are 1. Right? Had both J's not been 0, then it's true, the bound would have been J1 plus J2 plus 2.
Oh, 0, 0 is epsilon minus
Greater than 1. So that's why it's an A. It's on the bound, it's just above, a little bit beyond the short representation. Is this clear? Okay. Okay, excellent. Excellent. Now, so this determines all the characters. C-type is determined because we know the A-types. But now that we know the C-type, we know the B-type from here, because we know both A and C. Okay? And B-type, same argument. And this B-type, of course, we know. You see? Can't hear, sorry. Can what?
Can that null state in the final trial be
Yes.
DL or DR instead of A?
Cannot, because we know it's quantum numbers. It's 0, 0, 3. And 3 is larger than 1. Larger than 1. And therefore is an A-type representation. Because we know that the quantum numbers of the null state are p squared on the primary. Okay, so we just know the quantum number, so there's no discussion. That's what it is. Is it clear? Okay, excellent.
And quantum number is B is written as B as BL of 0.
B as BL of 0, I suppose you could do that. I suppose you could do that. It's just that B is a bit different. Its null state is not at level 1. It's at level 2. So, if you're interested in keeping track of the character of the thing, it's better to treat it as separate. It's got a different character from BL of 0. If you took the character of BL of J and analytically continued to 0, you wouldn't get the right answer.
Because C is there and here is
Exactly, because the null state of BL occurs at level 1. Whereas this null state occurs at level 2. So it's a different subtraction. Okay, so it's better not to think of it as BL of 0. Okay, excellent. Now, one could ask the following question. One could ask the question, look, suppose I've got a quantum field theory and there is a special point in coupling constant space. Let's say 0. You know, I've got a free conformal field theory, let's say. Okay? Now, if I take, and I know my state content at the special point in coupling constants, for instance, because it's a free theory. Okay? Now, if I take my my coupling constant and start moving it away from 0, can I say anything about the state content of the theory? Can I say anything about the state content of the theory, assuming that the Hilbert space or the full partition function of the theory is a continuous function of the coupling? At first sight, it might seem that you should be able to say something. This is because short representations, as we see from these formulae, have fewer states than long representations. Okay? And so, if short representations are going to become long, They have to do so by combining with something else. In fact, these formulae tell us exactly what they have to combine with. If I had a C-type short representation and its energy was to be renormalized, so that its energy went from J1 plus J2 plus 2 to J1 plus J2 plus 2 plus some small number, then it would have to become an A-type representation. Okay? But the A-type representation at 0, that's this, at epsilon equals 0, has the state content of the C-type representation plus the state content of this A-type representation. So this would have to eat up one of these, some other A-type representation. Only then can its energy be renormalized. Okay? So, yes?
You're moving away from the fixed point, but now again not conformally.
No, not fixed point. I'm moving away from the free point. Let's say I'm in a theory like n equals 4 Yang-Mills. We have a line of fixed points. Okay? So, I'm moving away from the free theory but remaining conformal. Suppose I could do this. Actually, I'll give you an example where this is useful. At some point. But okay? So, one thing you already see. You see that this representation here cannot be renormalized unless the state content of our theory has one of these representations. Okay? If that is not there in the state content of the theory, then this C-type representation will remain C-type. Okay? Similarly, the B-type representation cannot be renormalized unless there is this C-type representation which is there to be eaten up, and so on. However, these statements are less powerful than you might at first think. This is because typically, we have no control of what the A-type representations are doing. And typically a quantum field theory will have, zillions of these A-type representations. So, as we vary a coupling, an A-type representation might well come, even if it wasn't there initially at coupling equals 0, as we change the coupling, an A-type representation may well come down to this point. Because these guys are uncontrolled, right? Because their state content is independent of their energy. This A-type representation may well come down at this point to create, to be able to lift this representation. Or equivalently, what could happen is an A-type representation, if we didn't have this kind of C-type representation to start with, an A-type representation could come down and split up into the C-type representation and this A-type representation. And then the new C-type representation could go and renormalize this B-type representation. Okay? So though this, and similarly for all of them. So though these statements that I made are true, the fact that the statements always involve either long representations on the right hand side or representations that can be created out of long representations means that this representation theory gives you actually very little dynamical control over the quantum field theory, since you cannot control the long representations. They can do whatever they want. And this splitting here, the unfortunate thing from the point of view of control is that this splitting involves long representations, which means that C-type representations cannot be controlled because they can be created from long representations that come down and split into two C and another long representation, which means that this splitting cannot be controlled, which means that this splitting cannot be controlled, and this never could be controlled. So unless you have some large control over your theory that tell you that somehow these A-type representations, some independent controls, cannot come down and do interesting things. Unless you have that kind of control, this conformal representation theory, while first promising as a tool for creating non-renormalization theorems, is not delivering on its promise. Now, Let me tell you, by the way, that there is one interesting theory in which we have very good control over these A-type representations. These are matter-Chern-Simons theories with the matter and fundamental representations in D equals 3. And there, this conformal representation theory was used very simply to prove non-renormalization theorems for the primary operators in these theories as a function of 't Hooft coupling at the limit of large n. So, it's not like these things never give you interesting non-renormalization theorems. But it's just that they can only give it to you when coupled with other control over the theorem. It's an interesting fact, but not by itself enough to prove non-renormalization. I hope I've been clear in this part. Is what we hoped to do clear? To be able to argue that if there was, let's say, a C-type representation, BL-type representation at some value of the coupling, it or some remnant of it must survive at all values of the coupling. That's what we hoped to do, and we failed.
Sorry, what is this remnant of this?
I'll give you an example. For instance, the simplest would be that this B-type representation just has to survive.
Yeah, it will not change.
It will not change. I'll show you as we go along this class. You will see that things are not always as simple as this doesn't change, but something. You'll see. Diksha, yeah.
Similar to the question Siddhartha was asking. But you are changing the coupling in a way that the theory still conforms.
In everything I'm doing, I'm changing the coupling in a way that the theory still stays conformal, which I agree is an unnatural thing. It's very rare that you can do these things. However, sometimes it's possible. For instance, in these matter-Chern-Simons theories, one could do it. Okay? And of course, in superconformal field theories, one can often do it. Like n equals 4 angles. Okay? ABJM theory is at large n and large k is another example where you could sort of do it. Because in that limit, though the coupling constants were discrete, the large and large k limit is effectively lambda that's controlling the coupling. That's continuous. Okay, so there are some examples.
Do these relations are they useful there?
For ABJM theory? Well, ABJM theory, no. But ABJM, not these, but ABJM theory, the theory was superconformally invariant. And the superconformal analogues were useful, yes. Okay. Yes, okay, great. Excellent. So, we've looked at the conformal theory, we've understood its representation theory, we've seen how short representations were potentially promising for proving non-renormalization theorems, but somehow didn't deliver on their promise. Okay? Yes. Up in what? In energy and down in energy. Yes. Both ways there's a problem. Because if you can't control things, they can do whatever they want. Unless you have some other notion of control. Just from this representation theory, it's not good enough.
And just one.
Yes.
What is this non-renormalization theorem?
Non-renormalization theorem would be a statement like you take an operator which has a scaling dimension at some particular point in moduli space. Moduli space is the coupling. And then that its scaling dimension cannot change as a function of coupling.
Only for set of operators, not everything.
Not everything. For some special operators. Those, we might have hoped that those that were in the short representations could not change. That's the kind of hope we might have had, and you see it doesn't work.
So this identifying these operators is the problem. Right? Which
The problem is that, at a special point you might discover there are many short operators. But how do I know they remain short as I move away from the special point?
True. That sort of.
That's
how many genuine delta constant thing operator is there?
Yes. Now the hope was that you would have used the fact that the representation content jumps to argue that you cannot in a continuous way, the field theory state content would jump if it was renormalized.
True.
But you see that there is a way for it to get renormalized without the jump. For instance, so the C type can get renormalized by combining with one of those other A types. So unless you can somehow argue that those A types cannot be there, and typically you cannot make such arguments because you cannot control these long representations. Okay? It's not very useful so far. Is this clear? I've explained all of this to you.
So you are saying if these states are there, then there is a possibility that you turn on a coupling constant and C
will jump.
Also is this and
creates a huge long representation.
Exactly. So maybe I should have written these formulas without the minus signs but taking them on the left hand side. So C plus this has the state content of this. So it can combine together and then get renormalized. Okay? So this representation theory of the conformal algebra, while initially promising, largely turned out to be a dud from the point of view of non-renormalization theory. As I say, this statement is not entirely true, but largely. Okay? Fine. So let's graduate from the study of the superconformal algebras to the conformal algebras to the superconformal algebras. Yes.
What representation will it form after these two combine? Because you said that was meaningless, right?
Well, epsilon equals 0 is meaningless, but what it does is combine this, and then because there's a coupling constant, gives you this with some small epsilon. So it gets renormalized.
Okay, after renormalization.
Yes. So at the zero coupling, it's that plus that. But at any non-zero coupling, these two have combined into the A with a little epsilon. And the coupling is the thing that gives you the epsilon. Energy renormalization. Right? Okay? This can happen, and it often does happen. For instance, in a scalar free field theory, let's say n equals 4 angles. The scalar obeys the equation at the free point, which is del square phi is equal to 0. At the interacting point, del square phi is not equal to 0. Del square phi is equal to something, which tells you that this thing is coupled with something. The thing it's coupled with is the thing that appears on the right hand side, let's say phi cube, and has lifted. So it's not just a theoretical possibility, it often happens. Okay? Very good. Okay, this is a little similar to the Higgs mechanism, eating up states and getting more.
Del square phi is not very good analogy with this thing. It's like.
Why not? It's exactly this with the B-type representation. Del square phi was equal to 0 was a B-type representation.
Was the null.
Okay, del square phi was the null state, was this guy.
And now it is not null, it's added with something.
Yeah. You know, typically, let's say you had a theory like phi to the 4 theory. Del square phi will now be phi cube. Phi cube is a dimension 3 operator at the free point. So that's a dimension 3 operator, which combines with this dimension 1 operator to make a long dimension 1 operator. Okay? Fine. Now let's move on to study the superconformal algebra. Okay. Fine. Now if I can read this. Superconformal algebra, let's say that we have that our states are labeled by J1, J2 and some SUM. Some SUM Young tableau. Because UM, in general UM Young tableau. It will be SUM in the case m equals 4. Right? This you remember from an energy. These are the labels for primary states now for our superconformal algebra. This you remember, right? That the R symmetry was UM in general and SUM for m equals 4. Okay. Now, this UM is an SUM times U1. Okay. And what we do is to take the state and you act with Q on J1, J2, that the UM labels, tilde are the labels of the Young tableau, okay, and epsilon naught. Okay. Now what were the quantum numbers of Q? Q was, so now we're in D equals form, So we have both chiral and anti-chiral Qs. There are the Qs and the Q bars. You remember? Qs were SU2 left spinors. Q bars were SU2 right spinors. Okay? Because in this special case, SO4 is SU2 times SU2, the Qs and Q bars are largely on their own trip. Because one of them acts on the SU2 left, the other one acts on the SU2 right. Okay? So let's look at first what you get by acting Q on J1, J2, and this UM. And by the way, these Qs were in the fundamental representation of UM. Right? This you remember. Okay? So suppose I have a Qi. So what was the state content of this Q? Under J1, J2 UM, it was half, 0, and 1 box. And of course it had dimension half. Okay? Now, this guy I'm going to label by lengths of rows of the Young tableau. So this I'll call R1, this I'll call R2, this I'll call R3. And so on. That's the label for SUM. The UM is just the total number of boxes in the Young tableau. The U1 charge is the total number of boxes in the Young tableau. Okay? So, the most dangerous, so what do you get when you act with this and this? Well, J1 can go to J1 plus minus half. Something special will happen when J1 is 0. But in general, it can go to J1 plus minus half. J2 will remain J2 because there's no J2 here. Okay? And this UM goes to whatever you get by the Klebsch-Gordon of this guy with 1 box. Now, you remember that the most dangerous guy was when we made it the biggest possible R-symmetry representation, but the smallest possible angular momentum representation.
Sorry, what is this UM tilde?
UM tilde, I just meant the quantum numbers, so now I'll just change it to Ri. The row lengths and R, which is the U1 charge of this tableau. Okay, so I'm breaking up UM into SUM times U1. U1 is just an integer. And SUM is this other stuff. Okay. Now, you remember that the most dangerous representation, the most dangerous level 1 descendant was the one in which you added to you made the R-symmetry representation bigger, but the angular momentum representation smaller. So the most dangerous guy, so we have 2 cases. Single box, yep.
What is the Ri's and capital R?
Ri, R1 is equal to 1, all other little r's are 0, and capital R is equal to 1.
Okay, it's like addition of all the...
Yeah, r's are the number of boxes in the rth row.
But what is capital R?
Capital R is just number of boxes. Yeah, addition.
So then it's not independent.
It's not independent except that you have to deal with these UN Young tableau. You know, you can make these columns of length. Okay, let's take a minute. You know, you could have this, right? You could have m boxes in one column, which is not part of an SUM column, Young tableau, but carries U1 charge m. Okay? So the U1 quantum numbers are determined by the SUM Young tableau mod m. Because you can always add these filled columns or subtract them. Right? These are baryons. Baryons have 0 charge under SUM, but charge m under UM, under the U1 of UM. So mod m, the U1 charge is determined. Okay? That's why it's actually independent. So it's good to keep track of it separately. Okay? Though it's a subtlety that won't worry us too much. Yeah. Okay, excellent. Okay, so now, yeah. So now, what are the quantum numbers of the null state? So the quantum numbers of the null state, let's assume J1 is not equal to 0. Then the quantum numbers of the null state are going to be J1 minus half. I mean, of the most dangerous null state. Of the state that might become, the state that will first become null. Right? J1 minus half, 0 remains 0. Then R1 plus 1, R2, R plus 1, and epsilon naught plus half. What? J2, which remains 0, because Q doesn't carry any J2. We're looking at the action of Q, not Q bar. Okay, there will be a whole parallel story you can run with Q bar, which we'll talk about.
Is J2 0?
Oh, I'm sorry. J2. Thank you. Not J2 minus half because Q is a spinor under SU2L, but is a scalar under SU2R. Unlike P, which is a bispinor under SU2L times SU2R. R1 plus 1, R2 unchanged, R3 unchanged, and so on. And then the capital R is changed by 1. Capital R plus 1. Is this clear? Okay. Excellent. So now we can work out the norm of this state. Okay? Simple calculation. You work out the norm of the state and you find that this is equal to E. Okay, I sometimes use E instead of epsilon. In this paper I've used E instead of epsilon naught, so I'll call it E. Okay. E. Okay. Minus E1 J1 Ri Ri, where E1 J1 Ri and Ri is equal to this complicated looking formula. 2 plus 2J1 plus 2 into summation P is equal to 1 to M minus 1
Here this capital R and small r. Yeah.
Yes, that's the problem. Sorry. So in this paper, I'm sorry, I've used R1, I'll stick to that, R2 up to Rm and little r as the U1 charge. Sorry for that. Okay, so this has no R index, I index, but this has an I index. So 2 plus 2J1 plus P is equal to 1 to M minus P Rp divided by M plus R into 4 minus M divided by 2M. Just one thing. Oh my God. I'm so sorry. Here in this paper I've used number of columns of length. Let me give you the right labeling. I'll just tell you what R's are. No J2, because J2 doesn't participate. Because J2 quantum number is not changing. Because Q is not charged under SU2R. But let me just tell you what these R's are. M is SUM. Our R symmetry was UM or SUM. But let me just give you the RM is equal to RK is equal to number of columns of height K in the Young tablet. Okay, so now go on. R1 plus 1 and Rj. That's correct. So what is, I want to know the quantum numbers of the null state. I gave it to you in the labeling where I was labeling it by row length. So this will become R1 goes to R1 plus 1, R2, M minus 1, R plus 1, epsilon naught plus half. Right, because I add, right at the end of the tableau, I add one more box here. So if there was one column, one guy of length 1, will now become 2.
But previous representation was also good, but you have to change this formula.
Exactly. I've written the formula in this. You have to choose some. Yeah. There was nothing wrong with it conceptually. It's just what you've chosen. Okay. And this was the formula for the C1. Okay. So let's see if you understand this. This is 2 plus 2J1. That's sort of familiar, right? It's kind of thing that appears in the conformal algebra. And then plus 2 times the summation. The summation of these R factors weighted by M minus P divided by M. Sort of complicated. Plus little r into 4 minus M divided by 2. Just what you get out of algebra. Looks unnecessarily complicated, but what to do? This is what you get. Okay? Notice one nice thing. When M is equal to 4, the little r term drops out. Which it should, because at M equals 4, that guy decouples. The U1 decouples, right? The R symmetry becomes SU1. Okay, all good. What? For M equals 4, the R symmetry is SUM, not UM. So there's no U1 charge in the game. So this formula carries on even for M equals 4. You don't have to do something special there. The thing wasn't there, but it appears with coefficient 0. Okay, great. Very good. Okay. Okay. Now, of course, you can also ask what happens to level 1 states with of the form Q bar acting on a primary. What happens there is obvious, right? Just the role of J1 and J2 are interchanged. Okay. We're not even going to write that down specifically. Fine. Now, we need to say what happens in the case J1 equals 0. Okay. In the case J1 equals 0, First, at level 1, you get the following thing. You get 2 chi square is equal to E minus E1 plus 2. And the reason, as before, is that instead of lowering J1 by half, you have to raise J1 by half. That gives you a higher thing. Okay? So this gives you a higher thing, a less stringent thing. The most stringent thing is the most negative guy. You will get the most negative guy by lowering J1s. Here you didn't have that option, so you got a plus 2 there. Okay, but also as before, in the case J1 equal to 0, there is some new condition at level 2. You act 2 Qs on the primary and you get a new level 2 condition. And the thing that transforms in the smallest, the thing that gives you the condition is the guy with energy, of course, increased by 1. So how am I labeling it? J1. So it gives you, it's the one with 0 J1. J2, of course, nothing has changed. R1 has increased by 2. The remaining Ri's have not changed. And R has increased by 2. And of course, epsilon naught or E has increased by 1. This is very intuitive, right? Because you see, Q, the first time it acts, has to raise J1 by 1. But we know that it likes to lower. So the next time it acts, it lowers J1 by 1. Okay? It likes to raise the R symmetry charges as much as it can, so it raises R1 by 2. Okay? J2 is not in the game and E is raised by 1. So this is the primary state that gives you the new condition at level 2, and in this case we get that the norm is proportional to E minus this quantity, this whole quantity. Let's call this whole quantity E1 tilde. For the case J equals 0, we're going to call E1 tilde.
That's minus E1 plus 1.
Right. This, you're right. So this E1 tilde will be E1 minus 2. Thank you. Okay, let me check that. No, I'm sorry. This is just E1. I'm sorry. Just this E1, just E1 at J equals 0. Just E1. Okay, no 2. It's this one. 2 plus whatever else.
But RPs are not there.
What?
RP.
Why aren't RPs there? J is 0. SUN charge could be anything you want. Okay, so E1 is just whatever. So, sorry, with that E1, you get E minus E1 into E minus E1 plus 2. Okay, there was such a term, but okay, fine. Okay, so this tells you that in this case, this is the norm of this state. Primary. Okay, remember that this was the norm at level 1. Right? That was this thing. Okay, but in addition you get this extra piece here at E minus E1. Okay? So let's plot the positivity of this as a function of E. Let's plot this function as a function as a function of E. This guy here is so let's say we've got E1 and we've got E1 minus 2. Okay. So what we have, I'll just make sure I've got this E1 correct, just one minute. Exactly. So we've got E1 and E1 minus 2. So what we have is that this quantity here is positive here, and it's potentially positive here, but it's negative here. Okay. Now higher norm, when you look at higher orders, not second order but third order and so on, this range gets ruled out. But what you have allowed is this one guy here, and then this whole window coming here.
What gets ruled out?
What gets ruled out? All E's lower than E1 minus 2.
Why ruled out at first order?
Why is it? It's okay, good. Already at first order, you're right. Already at first order, it's ruled out. You're right. So this condition was, thank you, E is greater than or equal to E1 minus 2. Absolutely, you're right. Already first order tells you that this is ruled out. So this, everything had to be larger than this. But at second order you find that everything has to be larger than either E1 or just to be equal to E1 minus 2. There will be a null state, correct. It will be a short representation. Okay? So at j equals 0, j1 equals 0, you see that the state content of our theory is quite rich. Okay? You have two kinds of short representations. We have the short representation at energy E1, and we have the short representation at energy E1 minus 2. Okay? You know what's going on here is this, that the generic guy, j not equal to 0, always has to be greater than this, already at level 1. Because we couldn't make the most stringent thing at j1 equals 0, we got a less stringent condition that is greater than or equal to this at level 1. Then level 2 came back and made us realize that there were more stringent conditions, but in this quadratic way. Okay, the quadratic way was this equation. So it told us things had to be greater than here. We already knew, as Sunil pointed out, they couldn't be less than this. But it left this one little possibility, that E was equal to E1 minus 2. Is this clear? This, of course, as I vaguely talked about this last class, but not so specifically. And this is going to be very important, as you will see. Okay? Now, okay. Fine. So, now we're going to write down character formulae for the superconformal algebra and try to see if they give us more interesting dynamical information than the conformal algebra did. Is this okay? Okay, excellent. Notice that, by the way, that this guy is special because of all the representations we've looked at, it's the only one that is not or at least of the ones we've seen so far, it's the only one that is not the limit of a long representation. This guy is a short representation that can be reached as a limit of long representations. But this guy is just on its own kick. It's separated from a gap by all long representations by a gap. Okay, that makes it somehow special. Okay, excellent. Fine. Okay, now we're going to do some we're going to name representations. Okay, we're going to use the symbol XL, XR, okay, to label representations. Now, what XL is equal to A if E is greater than E1. XL is equal to C if E is equal to E1. And for any J, for J1 greater than or equal to 0. And XL is equal to B if E is equal to E1 minus 2 at J equals 0. Similarly, we have on the right XR is equal to A if E is greater than E2, where E2 is the J1 goes to J2 flipped version of E1, is equal to C if E is greater than, is equal to E2, and for any J2 greater than or equal to 0, and B if E is equal to E2 minus 2, J2 is equal to 0. Okay. So a representation of the form AA is a long representation. Okay? Anything else is a short representation. Anything else has at least one null vector. And now it's possible for representations to have two kinds of null vectors. Both a null vector from Q as well as from Q bar. That would be, for instance, a CC kind of representation. B's denote that we have J1 or J2 equals 0, and we're at the special isolated point. Is this clear? Okay? Now, what? E2 is coming from Q bar, and it's the same formula as for E1, except with J1 and J2 flipped. Right? Because Q bar and Q. Oh, I'm sorry. There's also the R symmetry. Let me write down the formula for you. R symmetry, right? Let me write down the formula for E2. You're right. Let me tell you about the right. For when we do the Q, you see, as Schumann reminded us, these Q bars are in the anti-fundamental of SUM. Q's were in the fundamental of SUM, so Q bars therefore in the anti-fundamental of SUM. Now an anti-fundamental in Young tableau is a row of length m minus 1. So instead of adding 1 to R1, it adds 1 to R m minus 1. It adds one more anti-fundamental box. Okay, so when you act with Q bar on the primary, you get a state whose representation is J1 is the same as it was, J2 has gone to minus half, R1 has remained what it is, Rm minus 2 has remained what it is, but Rm minus 1 gets one more. Okay, little r goes down by 1, and epsilon goes up by half. Okay, these are the quantum numbers of the state that you get by acting with q bar on the primary. Okay, and correspondingly there's a formula for E2. E2 is equal to 2 plus 2J2. Now this the SUM part is different because we've added, instead of adding 1 to R1, we've added 1 to Rm minus 1. So we get plus 2 into P is equal to 1 to M minus 1 PRP. That M minus P has been replaced by P. M, it's really a row, a dual tableau kind of thing, where you look at unfilled boxes rather than filled boxes. Okay, minus R into 4 minus M by 2. Okay, so similar story to E1, except that we have anti-fundamental Q rather than fundamental Q, and it has R charge minus 1 rather than R charge 1. Okay, so fine. Okay, fine. So now we've got these representations which are XL, XR, which are can be of the AA type, AB type, AC type, CA type, CB type, whatever. Is this clear?
For E equals to E1 and J1 equals to 0, I mean, this representation is not at level 2, right? So this should be level 2.
For E is equal to E1 and J1 is equal to 0. Yes, it's null at level 2. Correct. Good point. We should have. In all the relations that I'm going to talk about, though, it's true, we should. Had we been a little more careful, we would have done that. We would have done that. Exactly like, as you say, B was treated special in the exactly like B was treated special in conformal algebra. It's true. If you want to write down a character representation, we'd have to treat it a bit special. However, for the chain that I'm going to write down, it behaves in the same way as the other guys. So you're right. We've not been careful enough, but because it doesn't matter. Hang on for a minute. Okay, but thank you. It's a good point. Okay, now I'm going to write down character formulae. Exactly. So I'm going to write down character formulae and then we'll check them. Okay, so let me write them down first. Epsilon goes to 0, limit. Epsilon goes to 0. Chi AA at E1 plus epsilon. So that's the energy. J1, J2, R and Ri. Okay? Claim this is equal to chi of, this is now going to become a CA, J1, J2, R and Ri, plus chi of CA, J1 minus half, J2 of course, R plus 1, R1 plus 1, Ri. What?
J1 should be 0, no?
Why?
Because you have a C.
C is J2 greater than equal to 0. Could be anything.
No, J1.
J1 greater than equal to 0. B was the guy with J1 equals 0. C was for any J1. B was the special guy at J equals 0. J1 equals 0.
So that would be obtained that epsilon not equal to epsilon 1 or J1 equal to 0.
Epsilon naught was equal to epsilon 1 minus 2 at J1 equal to 0. For every other one, it was greater than epsilon 1. Right? All representations had E greater than equal to epsilon 1. The special thing about J1 equals 0 was that it also allowed epsilon equals to E1 minus 2. Okay? So the really special guys are the B types. C's are the generic short representations. Is this okay? Fine. So now let's look at this. Let's look at this equation. This time I've written, instead of writing the short representation, something minus something, I've written as something plus something. So I've taken the long representation with the limit epsilon goes to 0 to the left hand side, and showed how a long representation, when it comes and reaches the unitarity bound, how it decomposes into representations. Is this clear? What have I done here? I've taken energy just above epsilon 1 and taken epsilon to 0. So there's a long representation coming and hitting the left-handed unitarity bound. Then it gives us a C-type representation at the unitarity bound plus the null state. Remember, the null state was at J1 minus half, J2, U1 R symmetry we added 1, and R1 we added 1, remaining Ri's didn't change. So these are the quantum numbers of the null state. What I need to demonstrate to you is that this null state is in fact a C-type representation. Okay, that those are the quantum numbers of the null state is obvious. What we have not yet seen is that this null state is not, let's say, an A-type representation, but is in fact C-type. Is this clear? This is what I have to show you. If J1 is equal to 0, okay, yeah, you're right. Let me here put J1 not equal to 0. This is your special case as you were talking about before. Let's deal with that specially. Yeah, you're absolutely right. Let me first take J1 not equal to 0. Exactly. Because J1 is not equal to 0, we can put J1 minus half. What's going to happen as you will see what happens when J1 equals 0. Okay, but let's first look at this case. Okay, what I want to do here is to look at this and see that it is in fact, as I'm claiming, a C-type representation. What that means is that the unitarity bound continues to be saturated in a C-type manner for this guy. Okay, but now see, unitarity bound is saturated is if E is equal to E1. Okay, and E1 was equal to E1 was equal to was equal to 2 plus 2J1 plus 2 into P is equal to 1 to M minus 1 M minus P or P by M plus R into 4 minus M by 2M. Okay, what we want to do is just this was obeyed by the primary. That's why it was a C-type representation. Right? We took the limit so that it became a C-type representation. So this was obeyed by the primary. Now we are acting with this Q, which raises E by half. To show you that this remains C-type, I have to show you that the right-hand side has also increased by half. Okay, so what is the change in the right-hand side? First, J1 has gone down by half. So that gives you the change. So delta RHS is equal to -1, that is from J1. Okay? Now plus 2. Now we're supposed to do all the sum of all of these, but only R1 has changed. So we should take P equals 1. So M minus 1, R1 has changed by 1, divided by M. Okay? And plus this has changed by 1, 4 minus M divided by 2M. Okay? So delta of RHS is how much? So it's -1 plus 2 minus 2 by M minus half plus 2 by M. Right? So the RHS has changed by half, but the LHS has also changed by half. So this null state remains C-type. This is the real difference with the superconformal algebra. We'll look at all the special cases that Trautschuh is interested in. But this is the real difference with the conformal algebra. In the conformal algebra, the first thing we tried gave us the short representation plus long. The null state is transformed in a long representation. Here, the null state itself is in a short representation. This is where we're going to get fun. Okay, great. But we're not yet done. Let's look at all the other special cases. Okay. Now, question what is the analog of this equation? What is the analog of this equation when J1 is equal to 0? Okay? So suppose we have J1 equal to 0, then what? Well, that's the question we want to ask. Okay, now we need to keep track of the null states of this J1 equals 0 state. Okay, so J1 was equal to 0, so that's fine. Now the null state, as you remember, occurred at level 2 and had we written it down upstairs, the level 2 null state? Oh, anyway, we'll write it down here.
You are saying 0, J2, yeah, you wrote it.
Wait, but right, exactly. We wrote it. Can you just tell me what it was? 0, J2, R plus 2, R1 plus 2 and all the Ri's. Yeah. This is this null state. Okay. Now, J1 was 0. So it was a C-type representation. So E was equal to E1. Okay. So E was equal to E1. So E was equal to 2 plus 0 plus 2 into this. This was true of the primary. Okay? Now the null state, left hand side is increased by 1. Half plus half, so 1. Gone.
J1 equal to 0, how do you decide whether it is C or B?
It's C if E1, if E is equal to E1 minus 2.
Yeah, but we just said it's E equal to E1 and we wrote down, like, how do you know from beginning that, okay, it's
We're looking at the C-type representation. The C-type representation, which is E is equal to E1. The B-type representation, which is a special guy, is E1 minus 2.
So we are saying it's in the C representation.
We're looking at what happens in the C representation. Now, you see there's no question to ask for the B representation. Why? You see, because this long representation can come and be the limit of a C-type representation. But it cannot come and be the limit of a B-type representation. Okay? So we can only ask this question for the C-type representation. Okay? Excellent. So suppose we do the same thing now, but at J1 equals 0. If we do the same thing now at J1 equals 0, this was the energy of the left hand side, of the primary. Now, delta LHS is equal to 1 because our null state had one energy greater. Okay? What about delta RHS? Well, you see, it remains J1 equals 0. So this part is not changing. All that we get is the changes from here. So it's very similar to the calculation we did before, except we're going to get additional factors of 2. So we're going to get 2 into 2, so that's 4 into m minus 1 by m plus 2 into 4 minus m by 2m. Right? Okay. So this guy is what? So this is 4 minus 4 by m plus minus 1 minus 1 plus 4 by m. This is equal to 3. Okay? So now what does it mean that this energy that the right hand side, so what do we get? We get RHS minus LHS is equal to 2, it's not equal to 0. Not long. If RHS is bigger than LHS, it looks like less than long. It's B type, because there's precisely a difference of 2 for the B type. So this was B. Okay? And so the analog of this, that character formula, the analog of this character formula now is chi A E1 plus epsilon 0 J2 R Ri, limit epsilon goes to 0, is equal to chi CA 0 J2 R Ri, that hasn't changed, plus chi BA Okay, chi BA, and this is 0, J2, and then this is R plus 2, R1 plus 2, Ri. Okay, so Trakshu, the reason that we did not give a special name to the guy with j equals 1, you see it is special. But the reason that we did not give a special name is this, that there is this chain which just continues with this guy, except that the next guy in the ladder is not the next C-type representation, but in fact the B-type representation. Okay? So let me explain this a little more. You can't approach a B-type. We approached a C-type and its null state happened to be in the B-type. That nobody can stop. It just is what happens. What happens, happens. It's not, you see, the first guy is the non-null states. The non-null states there's no long representation whose non-null states are a B-type representation, whose limit of non-null states, limit of positive norm states are a B-type representation. But the null states are whatever they are. And that was the B-type. Is this clear? Okay? But there is no subsequent equation for the B-type. This will become clearer now as I explain. You guys, 10-15 minutes extra today. Is that okay? Yeah. Okay. So, yes. But this is the analog of that. But instead of the null state becoming some random long representation, it becomes a fantastic short representation. The isolated short representation. Okay? Now, see what is happening. In this whole, on all these character representations, the Ri's, all other than R equals 1, are going along for the ride. J2 is going along for the ride. So Ri's and J2's are constants as far as this whole game is being played. Okay? What is happening? What's happening is that you take a long representation. Okay? You've got a long representation, and what you get is chi of J1. So I'm not writing the indices that are going along for the ride. I'm only going to write down J, R1 and R. Okay? So what you get is some long guy is equal to chi J plus chi J1 minus half R1 plus 1 R plus 1. Okay? So it's a chain. But you see, then you can do another long. The long with these quantum numbers. And that will give you chi of J1 minus half R1 plus 1 R plus 1 plus chi of J1 minus 1 R1 plus 2 and R plus 2. And then you can do another long, the long with these quantum numbers. Do you see? What you're getting is a chain where this and this is related, but this is also related to this, and so on. So what's happening? What's happening is that what is conserved along this line? What's conserved along this line is R1 minus R, and for instance, 2J plus R. These two numbers are conserved. Okay? But with these conserved, you get along this line of things that are related to each other. I'll explain what I mean by related to each other in a minute. Along this line, what you get is one parameter. Let's call that J, J1. J1 could have been 0, or half, or 3 halves, and so on. Okay? Now you see, as J increases, R1 decreases. R1 cannot go below 0. It's the number of columns of length 1. Okay? So there's one bound there. Also J1 cannot go below 0. So there is another bound there. So this the number of longs that relate the representations with given R1 minus R and given 2J plus R is finite. Okay? Is this clear?
At one end the equation will be this second.
Exactly. At one end it will be the second guy. Okay? So now you see that let's parameterize this chain by the value of little j, where, remember all other ri's are constant, j2 is constant, these two numbers are constant. And let's parameterize it by this value of little j, where let's say little j has a maximum value capital J. That's when R1 was equal to 0. Okay? So there's some J1 which runs from capital J down to 0 and B. Okay? Let's call B minus half just for, because at each guy J was decreasing by half. So just out of notation, let's call it B minus half. Okay? So what we have is this, that the number of J plus number of J minus half, this is free to change. Right, sorry. If the only way that now let's say that I want this guy to disappear from the spectrum. It was there in the spectrum, I want it to disappear. The only way it can disappear from the spectrum is if along with it that guy disappeared from the spectrum. Okay? Similarly, the only way this guy can disappear from the spectrum is if that guy disappears from the spectrum, and so on. Okay? So do you see that if we do the following, if we look at the following thing, minus 1 to the power j, n of j, okay, minus 1 to the power j, n of j, little j is equal to minus 1 to j, with all these other things being held constant. N of j is the number of representations of that sort. This will always remain constant no matter what long representations come down or go up. Because you see, suppose we have a long representation of this sort, let's say coming down from the heavens and coming here, it increases this by 1 but also increases this by 1. So it leaves this sum unchanged. Similarly, if I have this long representation, these two combining and going off, they can do that, but it leaves this unchanged. So along one of these chains, okay, along one of these chains, this quantity will always remain unrenormalized. Is this clear?
So what is J?
Little j is a summation index, and capital J here is the largest possible value of j along this chain. So instead of doing this, let me label it by R1 here. Okay, let's call this H. This was a constant. When R1 was equal to 0, J maximum value, so this was H by 2. There were things held constant, right? And little j has a summation range that depends on those constants. Minus 1 to the power 2j. Thank you. It should alternate in sign. Thank you.
So j skips by half.
J moves by half. That's why this minus 1 alternates in sign. Now, minus 1 to the power 2j, does somebody know a name for it? What? Fermion number. This was equal to minus 1 to the power f. Because by spin statistics theorem, J is half integral only on fermioning states. And is integral on bosonic states. So equivalently, you sum along this chain weighted by minus 1 to the power fermion number. So this is beginning to sound a little bit like a Witten index. Right? In fact, it is a Witten index. It's a version of the Witten index that is called the superconformal index. Okay, but before I go on to that, maybe we should do that next time. But first, any questions or comments?
Couldn't have defined an object like this in just two conformal,
We could not.
because there was no R present. There was nothing which was constant.
Yeah, exactly, because there were too many long representations appearing on the right hand side. What was really important here was that on every decomposition, it was long going to short plus short. Okay? So now we have no control, we are assuming we have no control over the longs. Longs can do whatever they want. So they can produce shorts. Or shorts can annihilate, but in pairs. What was bad about the conformal was that, look at the first guy. It was a B, sorry, the one above it. A C was A plus A. I mean, an A, or the way we're writing it here, an A is an A, C plus A. Okay? What's really different about the superconformal algebra? It's actually two things. First, that the long representation, when it reaches the edge of the unitarity bound, splits up into short. Not short plus long. Okay? And the second thing was that there was this existence of this terminal guy, which allowed the series to end. We had these J's moving all along shorts, and then the last guy, what happens when you act on J equals 0? Well, there was the special representation, this B type, which allowed it to end. Okay? So you see that there is this conserved, absolutely conserved quantity. This quantity is conserved without any reference to dynamics. As long as you've got a theory whose partition function is a continuous function of some parameter, and it preserves superconformal invariance, this quantity will be conserved. End of story. Right? Just because otherwise the number of states don't match. Okay? So, superconformal representation theory is extremely powerful. It gives you non-renormalization theorems. This quantity, how many non-renormalization theorems are we getting? Let's count. Well, how many things were constant along the chain? Okay? There were, let's say, so suppose we are doing SUM theory. Okay? If we were doing SUM theory, first J2 was constant along the chain. Okay? Then all the total number, so the total number will be M plus 1 plus 1, M plus 2 non-renormalization theorems. Do you see? Because there are these two additional constants, then all the Ri's, which were M minus 1, and then there was J2. So 1 plus M minus 1 plus 2. For M plus 2, for these M plus 2 charges, you specify any numbers whatsoever. For any specification of these charges, this chain, is constant. So what have we learned? We've not learned, so this is an answer to a question you asked, Shuman, at some point. We've not learned that in general, it's not in general true. Okay? It's not in general true that all short representations are non-renormalized. But if they're renormalized, there's some combination of them, you can say something about their numbers that cannot change. In particular, the value of this chain for every value of these m plus 2 charges is fixed. M plus 1 charges, did I do it wrong? You're right. SUM has m minus 1 Kartans.
So only n minus 2 rows go for a right. So
Yeah, you're right. There was J2, there was m minus 2, and there was plus 2, m plus 1, I agree. M plus 1 charges. Now, let's count the total number of Kartan charges in the superconformal algebra. That was m from UM, plus 2 from SO4, so m plus 2, okay, plus energy, so m plus 3. Total number of Kartan charges was m plus 3. And we've got m plus 1. For m plus 1 specifications of charges, we've got non-renormalization theorems. Now, we certainly shouldn't have expected m plus 3. Because all non-renormalization theorems have to do with short representations. And in short representations, the energy is always determined in terms of the other charges. So the representations that could possibly have been non-renormalized would have been m plus 2. Parameterized by m plus 2 quantities. All the charges except for energy. And then energy is determined in terms of those charges. However, we're finding only one n plus 1 non-renormalization theorems. Why? We're not getting the statement that each of these n's is conserved. We're getting the statement that one chain is conserved. So it's less conservation than you might have hoped for, but much more than nothing. It's not the statement that the numbers of all short representations are not a function of coupling, but it's one parameter less than that. Is this clear? Okay. Let me maybe just quickly tell you one thing and then we'll stop. Okay.
You're saying that I for the short representation, I mean, usually the argument will not work because there are too many long representations and you will anyway find out something which joins with.
Like this long could split, come down from heaven, make two of these guys. So it's cannot be that one is absolutely protected. And that cannot be.
A huge parameter reduction is.
It's one parameter reduction. That one parameter is this chain. This J. What? Nothing else. Now, I have simplified the discussion because I've pretended that the left is on its own trip and the right is on its own trip. Q and Q bar don't interfere. There are some more things you can say. Okay. For instance, you can argue that the number of BB type representations is absolutely conserved. This is because, what you can do is get the kind of mechanism you have is you start with a long representation on the left, and then that descends into a C type plus a B type. But there was no long representation that would have descended had the right also been B type.
Yes.
You couldn't have reached that if the right had been B type. So you will never get a BB on the right hand side of one of these things. So in the splitting rules, BB will never appear. And therefore, the number of BB type representations is absolutely non-renormalized. Okay? These are called half BPS operators. Okay? And their number is fixed. If you have one, it will stay forever. These are exceptionally protected operators. But the generic operator does this thing. There are one or two other special statements like this which you'll find listed in my paper. Okay, so some special operators just cannot be renormalized. But the generic operator is like this. Is this clear? Okay, now I wanted to say one last thing and then maybe we can basically stop this discussion. The last thing is this. All of this smells so much like a Witten index that you could ask, is there some nice trace formula that one can write down that captures the same information? Okay? Is there a nice trace formula that one can write down that captures the same information? And the answer is yes. I'm going to very quickly tell you about it. The answer is the following. Consider trace of -1 to the power f times e to the power minus, let's call it gamma I hi, where hi's are any of the Cartan charges of the superconformal algebra, but gamma i's are chosen. Gamma i's are chosen so that gamma I hi equals 0, where hi's are the charges of a particular supercharge, okay, which we will choose in some fashion. Yeah, I'll tell you all of this in detail next time, just giving you the flavor of it. Okay, it'll be q minus half something, some particular supercharge. Gamma i's are the charges of a particular supercharge. Okay. Gamma is otherwise free, except that they have to obey this one condition. Now, if they obey this one condition, the same argument Witten gave for his index goes through. Because for any state psi, there is another state, this q acting on that side. Because the chemical potentials vanish on that q, the chemical potential weighting goes through the q, but -1 to the f gives you a minus n. So, this trace here receives contributions only from those states that are annihilated by this q. Now, it's not surprising that it's easy to make states that are annihilated by q. You just take some state and add q on it. And because q square is 0, be annihilated. But the same argument goes through also for q's complex conjugate, namely for s. It's s. So this trace receives contribution only from those states that are annihilated both by q and by its corresponding complex conjugate. If you annihilate it both by q and its corresponding complex conjugate, then you have to be annihilated by what comes on the right hand side of the qs commutation relation. And that's a particular superconformal charge. I'll tell you about this in more detail. So that gives you a BPS bound. E is equal to something. Okay? So equivalently, this trace gets contributions only from those states that obey that BPS bound. And I will show you next class that this Witten index captures exactly the same information as all these traces, these chains that we've discussed just from the point of view of representation theory. Okay, there's a one-to-one map between the two bits of information. Okay, so the non-renormalization of these chains is much more conveniently from the point of view of physics worded as the non-renormalization of a certain trace. And why is it more convenient from the point of view of physics? So because traces can be computed by computing path integrals. So you say this chain, it sounds so abstract, right? But a path integral is something you can calculate. So the non-renormalization of this path of this partition function is, yeah. Okay, let's stop here.